let's begin. So meeting is being recorded. Yeah, this is, I think, the 9th in the Tunneling in QFT series. Very happy to have everyone here. We have Simone Blasi from Daisy in Hamburg, who is a postdoc in Hamburg, previously was a postdoc in Brussels, and before that in PhD in Heidelberg. Yeah, Simone has done some really interesting work on phase transitions and on exactly the topic that he's going to talk about today. I haven't seen him talk about it before, so actually I'm very interested and excited to hear him speak. So yeah, please take it away, Simone.
All right. Yeah, thanks a lot for the nice introduction. Indeed, yeah, so today I'm gonna talk about, by the way, so if you have any questions at any time, please interrupt me and, because these are online seminars, it's also nice to get some feedback during the talk. So please don't wait until the very end. If you have some questions, please just shout it. So today, yes, I'm gonna talk about the role of impurities in cosmological phase transitions. And yeah, maybe let me just get started. So, okay, just very, let's say, short introduction. Why we are interested in this kind of business? It's because we think that cosmological phase transitions have actually taken place in the early universe. And, I mean, of course, I don't have to motivate this much to this audience, but you get to this conclusion whenever you combine the idea of spontaneous symmetry breaking with the hot Big Bang picture, when we think that symmetries are restored at very high temperatures, and then while the universe cools down and expands, the symmetries are broken, and at that time we get a phase transition. Of course, from a phenomenological point of view, phase transitions are interesting because, they could be related to the open questions in the standard model. For instance, the antimatter asymmetry of the universe. You can also produce some dark matter with these phase transitions, and also very, let's say, exciting times to be living in, the possibility of observing directly these phase transitions in gravitational waves. So of course, this is all very exciting. If you just look at the standard model, though, you will not get any first order phase transition. This is just because with the standard model content, the QCD and the electroweak phase transition are actually not first order. So if we want to make them first order and get some interesting dynamics, we need to have new particles or new symmetries. But this also means that whenever we observe a signal for that, we are actually probing new fundamental physics, which, of course, it's very interesting. But all right, so let me get to the nucleation theory, which is basically the tool you need to describe first-order phase transitions in the early universe. And so here, I just wanted to show a couple of slides regarding the typical picture regarding bubble nucleation. So consider, let's say, a free energy, which, as a function of the temperature, develops a barrier between two vacua. In this case, this green point at phi equals 0, and another point at phi non-zero, where, let's say, some symmetry is broken. What you actually are after is to calculate what is the tunneling probability of this false vacuum to decay. And what is usually assumed, and it is, of course, a very good approximation in the early universe, is that this phase transition actually is driven by thermal fluctuations. And so that basically you, let's say, drop the Euclidean time dependence of your scalar field, which then just depends on the position. And on top of that, if you consider that your universe is homogeneous, it kind of enjoys a rotational symmetry. So when you actually look for the tunneling solution corresponding to your order parameter, you search for something spherically symmetric. So in the end, you solve something which is, just a spherical bubble with a certain profile given by phi. Once you obtain this spherical bubble, you can estimate the rate for tunneling according to the usual formulas by Cullen and Coleman and also Linde, which is the one I'm showing here, where you actually calculate the nucleation rate per unit time per unit volume. which has some exponential suppression related to the action of the O3 tunneling solution you have calculated. And then there is also a prefactor, which in this formula is simply estimated by t to the 4, but as we know, this is just a very rough approximation. Of course, there are corrections to this formula, but this is more or less the idea. You have some prefactor that you need to calculate and some exponential suppression. So at the end of the day, you have a very simple picture of spherical bubbles that then are nucleated and then expand where your phi is different than 0. But the question, so the central point of this talk is, what about impurities? So what happens if there is something in the early universe that breaks your assumption of homogeneity that underlies the ansatz of a spherical bubble? And so the idea of having phase transitions that are actually driven by some sort of imperfection or indeed impurities is something very, very common also for particle physics. So here in the left, I'm showing some artistic view of a bubble chamber together with a realistic picture. And if you think of a bubble chamber, what you have is basically an oversaturated vapor in this kind of closed environment. And whenever there is like a charged particle that crosses the bubble changer, it triggers the condensation of the vapor. And this condensation is actually what makes these traces visible. And so basically you can observe, let's say, the motion of charged particles in this environment. But also this idea, happens in much more, let's say, or if you want, in much simpler situations. For instance, if you can get some very pure sample of water, you can actually supercool it below 0 degrees. But then as soon as you reintroduce some perturbation in your system, you will trigger, let's say, instantaneous crystallization. And this is like a YouTube video where they trigger, crystallization with like a grape. So the question is, do we actually have such a impurity in the early universe? And the answer is yes. And also, this is something that has been pointed out, as you can imagine, a long time ago. And so here I'm just, showing a couple of quotes from these papers from the 80s, because they kind of give the, let's say, overall picture of what we are actually talking about. So in particular, this one by Steinhard is already stating that, if your universe contains a set of monopoles or vortices, which is, just another word for strings, this finite density of these objects can actually speed up the phase transition and would trigger something which is inhomogeneous, because it will happen only in the vicinity of these defects. And then, of course, this raises the question of whether you can actually have supercooling in the early universe. If there are some impurities, perhaps your calculation needs to be updated, and the phase transition will happen earlier than you would expect. And finally, there is also this comment by Witten in Cosmic Separation of Phases, where he basically points out the fact that if the phase transition is driven by impurities, what controls the size of the bubble is not the slope of the free energy, this beta over h parameter, but it's actually the mean spacing between the defects. So it already tells that the phenomenology of these phase transitions, of course, will be different. And okay, so the more, let's say, broad question one can ask is, okay, what is the nature of these impurities? What could be there in the early universe that catalyzes or triggers a phase transition? And there is some literature, of course, in this topic, and there is actually a lot of work being done for compact objects, which could then catalyze a phase transition because of gravitational effects. And so this is basically the idea of having some very massive, very dense, or for instance, like a black hole that just sits around in the universe, and then at some point a bubble is nucleated around it. And you can actually check or perform calculations of, let's say, how more likely this process is to occur close to the black hole compared to very far away from it. And there is also some more recent work done on primordial density fluctuations. Imagine that you have the temperature and which is related to the density of your inside your Hubble volume is not homogeneous, but it contains some fluctuations over some characteristic scale. In this case, your nucleation events, so your bubbles, will be more preferably nucleated in the cold spots, just because the rate is larger there. And so this picture shows that these stars are like nucleation events. You get all these bubbles clustered on the cold spots. But so what I'm gonna focus on today is the case of topological defects, which, you know, they can arise in theories where you break spontaneously certain symmetries. And in particular, today I will talk about domain walls and cosmic strings. And so here I'm a bit anticipating some of the results, just to show that what we are having in mind is, let's say, a universe where some domain walls are present in your Hubble volume. And then you want to actually calculate what is the probability of nucleating a bubble right on top of these domain walls. And since the domain walls break rotational symmetry, this bubble will look like a squashed ball, so basically an ellipsoid. And the same story works with strings. Imagine that there are some strings in your universe. The critical bubble that nucleates right on top of the string will not be a sphere, but it will be somehow elongated. It is more favorable energetically to take this shape. And okay, so this is more or less the topic of the talk. Now I will enter a bit more in detail, discuss more in detail the calculation and the kind of setup that we have in mind. So, but before going there, just a brief catch up on the topological classification, because the objects we're talking about are, they have some mathematical properties, which basically determines whether these objects form in your theory and under which condition. So the formation of the defect is basically related to the homotopy classes of your vacuum manifold M. In the simplest case of the domain walls, this pi zero of M is non-trivial, which simply means that your vacuum manifold, so the points, your possible vacua in the theory are actually disconnected. And the simplest example where you can get a disconnected vacuum manifold is something very familiar. Just a theory with, let's say, a double well potential for some real scalar field S. The vacuum manifold is just 2 points, minus Vs and plus Vs. And they are not connected in the sense that if you want to go from one to the other, you will have to cross this maximum of the potential, which is at S equals 0. And the domain wall is simply a classical solution of the equations of motion when you interpolate between this minus Vs and the plus Vs. And it's really a wall because you can imagine that this solution only depends on Z, whereas it is the same along X and Y. So it's really like a plane where the field at the center of this plane is trapped at the maximum of this potential. And so this tells you that actually there is a lot of energy that can be, concentrated at the location of the defect. So this is what the domain wall looks like. The case of strings is somehow similar. In this case, what you look at is the first homotopy class, the pi 1 of your theory. And it's basically shown in this cartoon to the right, that whenever you break a U1 symmetry, if your phase of your complex scalar field winds, or let's say it completes a 2 pi circle in a real space, then you're guaranteed that somewhere in between the field is actually forced at the top of the Mexican hat. And this region where the field is actually pushed to be on top is the core of the string. Okay, so these are our basic objects. Let's now make a connection with some particle physics model, because at the end of the day, we're also interested in connecting this kind of phase transitions with models that have been considered, or that are related to the standard model and extensions thereof. So let's take probably the simplest model that has been considered to turn this electroweak phase transition from a crossover to a first order phase transition. And this model is known as the XSM. What you do, you just take an extra scalar degree of freedom, which is real, and you basically write down all the possible interactions at the normalizable level between this extra scalar and the Higgs. And you further impose a Z2 symmetry on the scalar, which basically, relates S to minus S. Of course, this will forbid some couplings that you can write in this potential, such that this symmetry is preserved by the Lagrange. And so the model is very simple. It contains just, two independent parts of the potential for the Higgs and this extra scalar, plus a portal interaction that respects the Z2 symmetry. So this model, you see, it's very economical. It really requires few more parameters, and it actually can make the electroweak phase transition very strong. So the way I'm actually writing the potential is by, making a very brutal approximation where I just include the thermal corrections with the leading high T term. So for me, or let's say for the sake of this argument, all the thermal corrections just modify the mass of the scalar such that at very high temperatures, basically you flip the sign of this mass term. And the point that is favored at very high temperatures is just the origin here, where both the singlet S and the Higgs are at 0. So all symmetries are restored at high temperature. When you further lower the temperature, depending on the parameter, especially depending on the value of these coefficients here, CH and CS, what can happen is that the first direction to become unstable in this potential is the one along S, such that you form domain walls at a certain temperature because the vacuum of your theory becomes this one here, where the Higgs is still at 0, so electroweak symmetry is unbroken, but the Z2 symmetry is spontaneously broken. And then if you further lower the temperature, so this happens at the temperature T domain wall that I'm considering. If you further lower the temperature, you will start to see that there is actually a global minimum that breaks the electroweak symmetry at some non-zero value of the Higgs. And the phase transition from this point here, where the electroweak symmetry is unbroken, to the point where it is broken, happens at some nucleation temperature Tn. And this second step of the transition can actually be strongly first order. And of course, this is interesting because, by simply adding a scalar to the standard model, you can now have a strong first order phase transition with a lot of, phenomenological applications. However, the observation is that because of the Z2 symmetry that you started from in the first place, there exists a completely mirrored path that points in your Hubble volume can take. So basically, at the temperature T domain wall, rather than choosing the value with plus Vs, some points in the universe may have chosen values, let's say negative, minus Vs. And this is completely equivalent because the theory is Z2 symmetric. Those points will also undergo the same first order phase transition at the second step at the same temperature T nuc, okay? But the observation is, okay, when you did that, when these two regions, those that have chosen different values of plus or minus Vs form, you will actually have domain walls in between. And so the situation when the second step of the phase transition takes place is more like the following. In your Hubble patch, there are a certain number of domain walls, which separate the regions with plus Vs or minus Vs. So now, deep inside, let's say far from the domain walls, in both regions, you have a certain probability of nucleating a spherical bubble. And this bubble, it doesn't know that the other side of the, let's say, the other domain has chosen a different value of Vs. So very far from the wall, everything again looks homogeneous. And you expect that the tunneling will be dominated at the usual spherical homogeneous bubbles. But the question is, what happens at the interface between the two different domains? And so what you actually need to calculate now is which one among these two processes, namely the homogeneous nucleation and the nucleation that happens right on top of the domain wall, is actually faster. And so basically what you do now is instead of defining the usual, let's say, nucleation rate per unit volume and per unit time, you have to define now something which is a certain nucleation rate per unit surface on your domain wall per unit time. And once you do so, if you want to compare the homogeneous process with the seeded process, you will also have to take into account that the seeded process can only happen on the walls. And if you think of it, it's like a sub-manifold of the whole volume. So you will have to actually pay some stricter nucleation condition. So now, you see, now it's more or less a matter of calculating the probability associated to these two bubbles and see what actually, which process is actually faster. So basically now the challenge is, okay, let's evaluate what is the probability of this seeded bubble, which is now, let's say, has a different shape. It's gonna be some ellipsoid. Ellipsoid, which of course, you say it's rotational invariant if you restrain rotations on the domain wall surface. And so there are basically three methods to evaluate this nucleation probability. And so far, I'm mostly talking about the, let's say, the exponential suppression, so the tunneling action. And one is to solve directly the equations of motion for the system. So basically searching for a bound solution which doesn't have a rotational symmetry. The second one is to perform a sort of thin wall approximation that we know in some cases it actually gives more or less the correct result. And then there is a third method that we developed, which I like to call Kaluza-Klein decomposition, which basically aims to reduce this problem of seeded tunneling by studying the theory that lives on the domain wall. So basically this method wants to get rid of the basically the dimension orthogonal to the wall. So now I will discuss a bit these methods, what they are and what are the assumptions. So the first one, as I said, is like, okay, I want to calculate what is the Euclidean action associated to this O2 bubble. All I have to do in principle is to set up the equations of motion for the tunneling, like in the usual case. But now there are two main differences. So as I said, first of all, you are not searching for a spherical bubble. So your equation now has become a partial differential equation, which only depends on the a radial coordinate on the domain wall plane and on a coordinate, let's say, orthogonal to it, which I call Z. So first of all, the fact that it's not a sphere, of course, complicated your problem that now becomes partial differential equations. And on top of that, also your boundary conditions have changed because in the usual case, the false vacuum is assumed to be a constant background value for your field, let's say H0 and S non-zero. In this case, if you start to go very far away from the nucleation point, so very far away from the bubble, you are not in the vacuum. You actually have to recover the original domain wall that you started with. And so this problem at the beginning was looking a bit complicated to us because you see it has to, you have to solve the bound solution, but now it became like a PDE. There are two coupled equations. So as I will show in the end, we also directly, let's say, tackled this problem. But this is not how we calculated in the first, let's say, paper. What we actually did was to employ first a thin wall approximation. And this maybe I can explain a bit what is the idea behind it. So, what you are after with the thin wall approximation is a relation between the energy associated to a bubble as a function of your radius. And this works when let's say, the wall, so the region where the field transitions from the false vacuum to the true vacuum is very thin. And in this approximation, what you have is when you evaluate the energy of your bubble, you have a term which takes into account that in the true vacuum, there is a gain in your potential energy. So this term is negative and is proportional to epsilon, which is the potential energy difference between the false and the true vacuum, which of course shows that you want to make a bubble which is very big. On the other hand, there is another term which grows like a surface, so the R² term, which tells you that once you make a bubble, you will lose, or anyway, you will need some energy related to the tension of the wall. And if you think now so, and okay, if you now neglect for a second this sigma domain wall term, what you get is like this red curve, which describes then, so when you evaluate this at the maximum, it tells you what is the barrier, let's say, for performing your tunneling. But so what happens if you start nucleating a bubble that is on top of the domain wall? Well, if you think of the same, let's say, energetics of the bubble before and after nucleation, you actually see that because you nucleated exactly on the domain wall, you have an additional term in the energy of your bubble, which takes into account the fact that you destroyed some part of the wall due to your nucleation process. So basically, the intersection between an approximately spherical bubble and the wall is this pi r squared, let's say, circle here. And in this circle, there will be no domain wall. So you have gained sigma domain wall times r squared energy. And now if you include this in the formula for the bubble, you actually see that your activation barrier is lowered by the presence of the domain wall. And this is something, you know, very intuitive also, if you think of it in terms of what catalysis is, right? Simply reducing the activation barrier for a certain process to take place. And this reasoning is actually quite similar to the case when you actually nucleate a hole in string wall networks, for instance, for axion-like particles or axions. Okay, so this is, let's say, the most intuitive one, but you know, it of course relies on the assumption that the bubble is thin and that you can describe everything in terms of a couple of coefficients. So what we also developed in the first paper is this Kaluza-Klein decomposition, and the basic idea is that okay, there is a domain wall, an unperturbed domain wall in your let's say in your Hubble volume, and what you're actually after is an expansion of the fields around this domain wall. And you want to now separate, let's say, the dependence on the orthogonal direction to the wall and on the coordinates x mu on the wall in terms of some sigma k profiles in the case of the singlet and similarly in the case of the Higgs. So what you are basically trying to do is to describe your fields as some modes living on the wall times some profile functions which extend in the orthogonal direction, okay? And this, of course, you can simply do, and you can actually do it in a clever way, which is to actually diagonalize the spectrum of excitations of your domain wall. So this basically just amounts to you know, a good choice, let's say, of your profile functions, sigma k and phi k, such that these modes that live on the wall, so these sk and hk, they are canonically normalized. And if you do so, you basically end up solving some kind of eigenspectrum of states in the domain wall background. And what you actually notice is that this spectrum, which you can actually evaluate fully analytically because you can map the problem into, you know, a post-Steller kind of potential, which is exactly solvable. So what you actually notice is that, okay, these modes there are two different types of modes. Some of these modes are localized on the wall, and some of them basically correspond to what I would call like a Kaluza-Klein tower of continuous states, okay? And omega 0 is the mass of the Higgs, but for the mode which is really localized on the domain wall. And so what we actually did is to take, you know, this theory with a lot of Kaluza-Klein states and to bring it down to something which is tractable. And so I was saying before, the kinetic terms are canonical because of the choice of the profiles. But then you see, you have, in principle, on the wall, there are many modes that live there. But the idea is that at some point, there is a mass gap between the lowest modes and this Kaluza-Klein tower. So what we actually did is to integrate out all the heavy modes corresponding to this MKK and omega KK scale for both towers. to obtain an effective theory which lives on the domain wall. So as you can see, it's like a three-dimensional, namely two space dimensions and time, of keeping only as dynamical modes the lightest states, which are these H0 here and S0 here. And now these two modes will interact by some effective potential that takes into account their three-level interactions and the contributions also from these Kaluza-Klein states. And okay, why do you do this? Because at the end of the day, you manage to take your inhomogeneous tunneling to a homogeneous problem, but now one dimension less. And once you have this effective 3D potential, you can actually evaluate the bounce action simply by cosmotransitions. And so here I'm just showing a sketch of this potential where you see that you develop another minimum, which is away from the origin, let's say, that corresponds to the domain wall. And now the bounce action is simply, the optimal trajectory that takes you from the false vacuum to the true vacuum. And you can evaluate it, with all the precision that you want now that you have reduced the problem in this way. And of course, so once you have the tunneling trajectory for the two, let's say, lightest modes that live on the domain wall, you can reconstruct all the profiles that you started from, because you know all the relations among them. And now here, this bubble here is a bit of a cartoon of what happens, let's say, far from the domain wall, namely, let's say, a spherical bubble. But now, once you reconstruct these profiles, you see what actually happened. I mean, very far from the bubble, you reproduce the unperturbed domain wall. But really, at the center of the nucleation point, you see that the domain wall has basically deformed to make space for a non-zero Higgs core. And now this part here you can interpret as the seeded bubble that will then expand in all directions from this point on. And okay, now you can ask, okay, all these methods, but how do they compare to each other? And so this is what we did in this paper with Pratik and Michael. Because we included together with the thin wall and the Kaluza-Klein, let's say, method, a fully numerical algorithm based on this mountain pass theorem, which is a way to, find saddle points of partial differential equations, which is exactly what we're after. And so this is like a benchmark point where you fix, the portal coupling between the Higgs and your extra singlet, you fix the self-quartic coupling, and also you fix the mass of the singlet in the electroweak vacuum. And now you can actually compare the probability for nucleating the homogeneous bubbles with the probability of nucleating the seeded bubbles on the walls. And so what I'm showing here is this red line is the homogeneous S3 over T, together with its nucleation condition, which, approximately at the electroweak scale is something like 140 or so. So if you just look at, if you neglect the domain walls, okay, you would say that this phase transition has a nucleation temperature of 0.8. You will derive alpha, you will derive beta, and make a prediction for the gravitational wave spectrum. Let's now look at the seeded process. So as I was saying before, since now the nucleation can only happen on the domain wall, you have a stricter nucleation condition that you have to meet to have at least one bubble in your Hubble volume. And so this means that at the electroweak scale, the usual S over T 145 becomes actually something like 105 if you can only nucleate on a surface given indeed by the domain wall. And so here I'm actually plotting all the different predictions that we can make with the methods that I've described. And maybe I can start with the lower end of it. In particular so all these lines, the green, the orange, and the blue, are obtained with this 3DFT, which I know it's a bit unfortunate name because it looks like you do the thermal dimensional reduction, but this is dimensional reduction on the domain wall. And we can actually predict, in the way I was explaining before, the tunneling action to increasing level of accuracy by including more Kaluza-Klein states in our effective potential. And so there are three lines, the one where we pretend that there are no Kaluza-Klein states. Then there is the orange one where we integrate to accuracy 1 over m squared, and then 1 over m to the 4 is the blue one. And basically, you see that at some point, let's say at lower temperatures, they all agree. But if you increase the temperatures, it becomes important to include the Kaluza-Klein states in your calculation. But these lines tend to agree up to a point where the Kaluza-Klein theory actually can no longer describe the tunneling. And this is because, this kind of reduced theory, or let's say, imagining the seeded tunneling as a process happening in this lower dimensional theory only works if your bubble is actually more of a disk than a bubble. So namely, whether it works when the bubble is really much bigger on the domain wall plane than in the orthogonal direction. Around this point, the bubble is approximately spherical, and therefore your Kaluza-Klein expansion is not converging. And then you see that the predictions are different. So here we stop with the prediction. However, once you are very close to the critical temperature, you know that the volume effects are more important. So this bubble is going to look more or less spherical, but with some corrections, as I was showing before. And then this is the purple line that you can draw just with the thin wall formula I was showing. As you can see, there is basically a region in between where we don't really know what's happening, and that's when we use the actual solution to the equations of motion, really just to solve for the bounds numerically with no approximation, and these are the red dots. And as you can see, these red dots agree very well with the Kaluza-Klein theory at low temperatures. They also reproduce reasonably well, I would say, the thin wall very close to the critical temperature, and in between they provide the correct extrapolation. So this is for us, let's say, a cross-check of our methods and to see how they work. And especially for this benchmark, you actually see that the phase transition will not happen at T over Tc 0.8 as the homogeneous nucleation would predict, but it will actually happen much earlier, which is namely, let's say, the point where the numerical line crosses the seeded nucleation condition. And this is happening at 0.95 or so. So as you can see, this can change completely the phenomenology of your transition because the seeded process is actually much faster. And okay, so now I just wanted to show a couple of like implications just to say why this could be relevant. So first of all, if you look at this model for real, like this XSM model that has been studied a lot in the literature, there is typically a region, which in this plot is between the red and the blue line, where you would say that these points are all, let's say, not viable, not because the vacuum is wrong. There's nothing really wrong with the theory itself, but it's just that the tunneling is so slow that the universe will be trapped forever in the false vacuum. And so you would be tend to exclude these values of the portal coupling over here due to this argument. They would be not viable. But once you start including this additional decay channel for your false vacuum, you actually see that those points become available. So this extends the region of parameter space that you can, that it's actually viable in this model. And okay, if the domain walls are around, we found that the seeded nucleation is always faster than the homogeneous one. So basically, the homogeneous nucleation never happens in a realistic. I mean, once you really start considering both decay channels. And okay, this I'm not gonna discuss too much, but of course, what I was also mentioning at the very beginning, if the transition is driven by the defects, the size of the bubbles when they collide is simply given by how many defects you had in your Hubble volume at the beginning. And so this means that actually you can get very big bubbles if you imagine that there are only, let's say, 2 domain walls in your Hubble volume, which is actually what you would expect if the network has reached the scaling regime. And okay, we just also to mention that we did a numerical simulation, actually a fluidodynamical simulation of bubbles, being nucleated on the walls and how they produce gravitational waves. So this plot is actually not the end of the story, the one on the right, because this only takes into account the very late time contribution. So there is some work to do in this direction. But what we found is that, okay, the peak of the spectrum is shifted towards what you would expect from the domain wall network, let's say, correlation length. And there are also some differences in the spectral shape. That one, if you improve this analysis, you might actually try to see whether you can distinguish a homogeneous transition or a seeded transition in terms of the spectrum. So these are, just more phenomenological applications of this calculation. But yeah, so I also wanted to, let's say, show some ongoing work that I'm doing with Andreas Eksted, who is also organizing this seminar series, which is the following. So far I was showing like theoretical calculations of the standarding probability. But we know that with the help of numerical simulation or the lattice, we may actually be able to simulate this system. And then you can do many interesting things, like you can cross-check your theoretical predictions. You can actually see if things go as you thought they would, or if there are more effects that you should take into account, and so on. And so the let's say the basic idea that we have, or let's say the basic methodology that we are using, is some Langevin approach that mimics the presence of a thermal bath interacting with our scalar field or the parameter by introducing fluctuation dissipation in the equations of motion. So you basically take the equations of motion for your field and you add a dissipation term with a coefficient eta proportional to the time derivative of the order parameter. And on top of that, you include a stochastic contribution indicated by this term psi, which has some statistical properties. In particular, we take it to be a Gaussian noise, which, randomly will give some kicks to your scalar field in a way that should mimic thermal corrections. And this eta parameter, of course, takes into account that once you displace your field because of this plasma, it will take some time for it to go back to the original point, let's say. And so this dissipation and fluctuation term are actually to satisfy a relation which basically connects the two via the effective temperature that you want to simulate in your, let's say, in your system. And so so this is the overall framework. This has been used also for tunneling of, homogeneous bubbles. So what do? We basically, as I said, we want to perform real-time simulations of bubble nucleation. And the model that we have in mind is exactly what I was discussing so far. So a model with two scalar fields undergoing a two-step phase transition. And then we want to see whether the second step happening at Tn is actually, seeded by a domain wall, or it is instead much easier to nucleate in the bulk of the space far from it. And so what do? Is that, first of all, we choose a temperature, which is, let's say, after the domain wall phase transition has happened. And this temperature is actually quite small. It is of the order of the mass of the Higgs of this like a Higgs mode localized on the domain wall. So the prediction is that at this temperature, which is typically lower, it's typically lower than this Tn. And so let's say it's typically lower than the temperature where the homogeneous nucleation happens. And so basically, this is because the mass of the Higgs inside the wall is different than the mass of the Higgs outside. And so at this temperature, there is basically no way of nucleating homogeneous bubbles, or at least this is the expectation. So what do? Is that we initialize our simulation box such that there is a kink along this singlet direction, which should correspond to our domain wall. And the Higgs field is randomly initialized at the value h equals 0. And then what we do is to check for what happens, once you have evolved the system for some time. And what we find is that after a certain time that you can actually estimate to be related to the length of the box and the seeded nucleation rate, you start to see some bubbles that are formed in your system, and you can see them by eye. They correspond to these blobs here. And as you can see, all the bubbles that we find are really nucleated on top of the domain wall. And this, of course, makes sense with the idea that the tunneling is really speeded up by the presence of this impurity. So we never find bubbles being nucleated far away from it. And then now you can actually start to compare what you get from the data of the simulation with your theory prediction. And so here I also wanted to say that if you write your nucleation rate for the seeded process, this will contain the usual part e to the minus s, the exponential suppression, and I was already showing how you can evaluate the seeded bounce action with all these different methods. But now there's also the question of how do you evaluate the prefactor, right, for a seeded process. Typically, this prefactor has been estimated by just taking the tension of the domain wall, because somehow this is the scale of your impurity. So, it's actually maybe a good guess. But now I think that if you start using so if you refer to the Kaluza-Klein theory, you may actually be able to evaluate this prefactor by using the usual arguments, and actually the numerical methods that were presented in this paper. So the Kaluza-Klein theory could actually, since in this theory, you are able to discuss a homogeneous process, just one dimension less, you might be able to apply all the, the standard calculations to evaluate also the prefactor, which has never been done. And this is like a slide that I have with some preliminary results. So now I picked particularly, let's say, good plots. This is still something we are working on. But the logics is the following: like we start our simulation, we check when the first bubble is nucleated, and then we collect all the timestamps, let's say, of all these nucleation events by running, the simulation several times. So in this case, we had like 250 runs. And so once you put together all these nucleation events, you can have a survival plot for the false vacuum as a function of time, which basically tells you after some time how much of the points are still in the false vacuum or which instead have nucleated. And from this survival time, you can extract a rate, and you can compare it with the theoretical calculation that I was showing, which is performed within this dimensionally reduced theory. I should also say that the theory we are simulating is actually in 2+1 dimensions, because from a numerical point of view, it's of course much faster to simulate the one dimension less than the 3D case, but our idea is of course to extend it to 3D. In the 2+1, the domain wall is just a line, so it's really a one-dimensional object. Okay, so yes, indeed. So then, okay, by comparing with the theory calculation, you can actually see if it works. And so far we found good agreement, but what becomes a bit difficult to check, is the extrapolation to the continuum. So to take the continuum limit, namely the lattice spacing going to 0, or the infinite volume limit, namely simulating bigger and bigger, let's say, boxes. And also something that you have to start caring about is the renormalization of your parameters, which will depend on the lattice spacing and so on. And so this becomes a bit more difficult to do. Okay, so actually, I don't know how I'm doing with time, but I might stop here. I also wanted to cover the case of the strings, but yes, I think this is already, I don't know, enough. But if there are any questions on that, I can also talk a bit about this. But otherwise, I think I would stop here.
Okay, thank you very much. Thank you, Simone, for a very nice talk. Yeah. Any questions from the audience? Please raise your hand with, or just, let's go with raise your hand for now. And if you can't manage to do that, just unmute yourself. Okay, let me ask a question while we wait. So I had a question. So around your thin wall analysis, it seemed like you had assumed that the wall was also spherical. Is that right?
Yeah, so in
And would
this
it be
one,
possible to amend your thin wall analysis to apply to a different shape, like a different geometry, which is not spherical, but this ellipse or whatever you think it is?
yeah, we did it actually. So here I'm showing the spherical formula because it's more intuitive. But actually in the paper we have it with an ellipsoid with two parameters, just the two semi-axes. But it doesn't really change much. So for the sake of the approximation, I think because anyway, like the region where the thin wall works is close to the critical temperature, and there you expect it actually to be more or less a sphere. So we checked that at the end of the day, it doesn't really matter. But yes, in principle, you can do it. You can have an ansatz for your shape, which instead of R, will have two R's, and then you basically search for a saddle point in these two variables, the two semi-axes. So it's not a maximum, then it's a saddle point. Doesn't change much the conclusion.
Okay, thanks. Any other questions from the audience? Okay, we have one from Marek. Please go ahead.
No. Well, if there are no other questions, maybe a few words on strings. What sort of models were you thinking of?
Yes, so we took the QCD axion because we thought it was the best motivated. But of course there are I mean it's just to take one example, but the calculation, or let's say the properties, are very similar. So what we did in this paper, just to take like strings, so axion strings in this case. But as I said, I mean, this can be more general. What matters maybe is the shape of the potential that we took. Again, it's inspired by this, when you couple the Higgs with the Peche-Quinn scalar field. So basically you have a portal coupling between the field phi, which is the Peche-Quinn the Peche-Quinn field containing both the axion and the radial mode. And yeah, it has a neutral portal that is allowed by all symmetries with the Higgs. And so this is the model that we take. So it's very similar to the case I was showing with the domain wall. Instead of being like h squared s squared, now you have h squared phi squared. And okay, there is this normalization to get the correct vacuum when phi is fa and so on. But this is the idea. And okay, if you start with this potential, I mean, this is the minimal KSVZ axiom model with a portal, which actually is there. Of course, it's a question of how big the portal is. So, okay, this is a bit more technical, but anyway, once you have this kappa, you start to search for axion strings solutions, and you have more solutions than when you neglect the portal. Because, now the Higgs can also do something inside the strings. And now the electroweak phase transition is actually a transition from two different types of strings. Yeah, so I mean, okay, there's a lot of details here, of course, that I'm skipping, but I just wanted to maybe show, yeah, so like, maybe we can just show this. I mean, once you like take this model and you consider what is the nucleation of the most likely bubble, what you get is a shape of this type. So the red one is the typical axion string, and at some point you see that it starts to form a Higgs core of this type that expands eventually.
Right. Okay. Does that depend significantly on the? Because what do you assume about? No, there isn't. This is just one solution, right? So you don't talk about phenomenology. For
No,
example, do you assume the strings scale? What do they do?
the string, sorry, what?
Do the strings scale? I mean, how much before this the strings are formed? Before the nucleation process?
Mm, Wait, maybe I have something I can show. No, wait, okay, maybe I show this. No, so okay, all this assumes is just that there is the normal string. The calculation of the rate only assumes that there is one straight string, and then you can calculate everything. So of course, like it depends how many strings you have in your rubber volume, it will have a different phenomenology. Like if the strings are not in the scaling regime, there will be more strings, so the bubble size will be different once they collide. There are all these kind of things. But maybe another important thing is, okay, one thing that we do change and let's say take into account is what is the mass of the radial mode of the Peche-Quinn scalar. And we plot it against the value of kappa over eta. So what matters in this model is the parameters that really make a difference is the mass of the radial mode and this ratio. So it's not the portal alone, but it's the portal compared to the quartic self-interaction of the Peche-Quinn. And if you want, then we make a plot of this type where if you are in the white region, nothing changes. If you are in the blue region, things can change a lot. So like it's just a way to tell how big the portal has to be to have some effect from the axion strings. Of course, if the portal is 0, there's nothing, okay? But then depending on the mass of the row and this ratio, you enter this blue region where you can have some effects.
Okay. If no one else has anything, I have one more.
Yeah, there are no other questions in the room. Go for it, Marek.
This is a very small one, but you said when you were talking about the gravitational wave spectrum you produced that you computed together with Thomas and Yusuke.
Yeah.
You said that this is only a late time contribution?
Yes.
What did you mean by that?
Because so what let's say so typically let me maybe just get there. So typically what the biggest contribution to the gravitational wave spectrum comes after percolation. So after let's say all the spaces in the true vacuum, and because okay, you have these long lasting sound waves, right? They can typically last longer. And so the simulations are, yeah, of course, it's not always, I also had a plot about that before. But let's say the common idea is that if the main contribution comes from the sound waves, then from the simulation, you don't want to be contaminated by the early times when you extrapolate. So you basically want to isolate the contribution from the sound waves because that's what you want to have, and then you plug it in the gravitational wave formula, so you get a good let's say approximation. So to not have any contamination from what happens before, you actually neglect that part. But then in this case of like having a phase transition which is seeded by let's say the defects, I think it could also be very important to look at what happens at the early times, because the phase transition can also be very slow. If there are really, let's say, only few axion strings in the whole Hubble patch, the phase transition will have very big bubbles. It will take a lot of time. And so all the contributions, sound waves, early times, also notice that there are large violations of spherical symmetry from the very beginning here, because actually your bubbles are not bubbles, but are cylinders around the strings expanding. So these should be rechecked. But it would apply to cases where the phase transition is actually slow, where everything is more or less of the same order.
Right. But so what you're saying is just that the simulation only takes into account the plasma. There is no fields.
Of course, yeah. That's on top. That's on top of what I said. Yes, that's true. These are all Higgs simulations. So basically, you just decide how fast your bubbles will go, how much latent heat, and you get the spectrum. It's only the fluid, yes.
Right, but then I would think that well, at least the breaking of spherical symmetry, that's there, right? Because the bubbles, well, you can clearly see that there are those structures develop before the bubble collisions. So that is there.
Yeah, that is there, but the simulation, doesn't take into account this early stage. It only takes into account after everything has merged. So the snapshot I'm showing is not taken into account in the right plot, if you want, because this right plot is basically starts taking the gravitational waves only after all these red bubbles have collided with everything else.
Okay, well, maybe I need to read the paper more closely, but why not just integrate from this point?
Because I was saying, because you don't want to, so because the logic is the main contribution is from the sound waves. I want to get that number from the simulation, and I want to perform some sort of extrapolation to that, because here there is no Hubble. So I make the simulation in a way that everything I get is from sound waves, so then I can perform the extrapolation to, let's say, a long-lasting source. And so that's why we did it like this the first time.
So then you just neglect early times and don't, but
Exactly.
What I mean is that I think in every simulation you can neglect the early times, but that's just because you can just do the integral and you will see that then the spectrum develops throughout, and at late times it just looks like this. Won't it be like that here? You get something very strange from the early time contributions?
And we didn't check.
Okay.
That's
interesting.
Yeah, we didn't check that. We didn't check the early times. Because, as I said, if you think that the phase transition is fast, those early times are probably eventually, let's say, they will not be the most dominant contribution. So that's why. But you don't know.
But that's a guess. I mean, I would only not include something if there was a big problem. You're not telling me there was
No,
one.
there's absolutely no big problem to do that.
Okay. Thanks.
We've hit the hour mark, so let's leave it there. Thank you very much. Again, Simone, thank you, Marek, for your questions. And see you next in a month for Mark Hindmarsh's talk. Bye-bye.
All right. Thank you.